everyone, welcome to this video. This video is going to be very important in terms of time complexity and in terms of understanding that how time complexity varies with certain operations. So without wasting much time, let's get started with the video. So far in this particular DSA course, we have discussed that what is the time complexity for various operations and how do the charts look like. Okay, so let me just reconfirm few of the things because there was some discrepancy. So let us say this is our chart, this is our number of operations, and this is the data size in the x-axis. Okay, now let us say we have to create the ideal time complexity charts. So first of all, we know that is the time complexity O1, which is the constant time complexity, and it will look like something this because it will always remain constant with your data size. This is called O1. Now the second one comes little better than this, is generally known as log n complexity. So what does happen? So let me just so it will basically start from here and it will go like here. It will be very close to O1, but it is little. So this is O log n time complexity. Okay, so these two are very ideal time complexities that we have seen so far. The third comes the O n time complexity. So third will be O n time complexity. This is called the linear time complexity. After this, there was some discrepancy, so I'm just correcting few things that after this it will come the n log n time complexity. So how it will vary? It will go something like this. So this time complexity is O of n log n. This will be seen in very specific cases of sorting algorithms, merge sort, and there are some other sorting algorithms. So we will see these type of algorithms in those type of videos. And now after this comes the n square, the polynomial time complexity. So if you see, this will be your O of n square. Okay, similarly you can draw for n cube and for like it can keep on varying. After this comes the worst time complex, one of the worst time complexity, that is exponential time complexity. This is O2n. Now it could be 3n, 4n, 5n depending upon the scenario, but it will be, this is called exponential time complexity. And one of the time complexity, it is called factorial time complexity. It is not required to cover, but it lies somewhere around here. So it is something called n factorial time complexity, but we don't need to remember that. So this is the right order of time complexity that we have seen so far. Now there will be multiple scenarios that few algorithms, few coding, they of course it means so ideally for us, we should try to solve any question with O log n or O1. Okay, but there will be few questions which cannot be solved through these particular like whatever you try, you cannot solve using these particular time complexities. So you will have to resort to the, for example, n log n sometimes, and depending upon that particular scenario. So we will see that. This is just a quick summary of whatever we have discussed so far, and I hope this particular chart is clear. I just wanted to clear because in one of the video by mistake I mentioned n log n to be here, which is not the case, because if you see n, it means that it is greater than this, and log n, so this is n square, so n into n, and this is n. So n into log n should lie somewhere in between this, and because log n is less than n square, n, right? So that's why n log n lies here. So I hope this explanation is clear. Now let's switch to the main topic of this video, that is how does my time complexity varies with various operations in a list. So this video is mainly about that, and let's switch to that particular topic. So we know that list is a data structure in Python, and it has various methods involved. We have seen in previous lectures that we can add element to a list, we can remove element from a list, we can do slicing, and we can do a lot of operations. So we will be seeing that how does each operation changes the time complexity. So for example, because we will be using these methods throughout our course, right? So we need to know that each step corresponds to which time complexity, so that whenever in the course you are asked that you have to reduce time complexity, you know that okay, if for example if I have to achieve O1 time complexity, so I cannot take these particular methods, because if I use these particular methods, they will take the code to ON or some other time complexity. So let us just try to understand which all elements, which all methods are present in a list, and what all time complexities are associated with each of the operation. Okay, so far we know the major big O's that we have: O1, ON, O log n, ON square, right? O n log n and exponential, they are used very rarely. They're not used heavily, so I'm not considering them right now, but we will be seeing them in the future. So let us say the first operation is talking about indexing. For example, let us say we have a list. So what do we have? For example, here we have a list which has 5 elements, and the list name is list, and these are the indexes of the particular element 0, 1, 2, 3, 4, and these are the right elements. The first task that is with us is, what if I want to access an element in a list? Okay, now accessing can be done through two methods. Either I can access it by index, okay, and or I can access it by the actual element. So let us see how does it look like. Right now, let's see that, for example, if I have to access this element 40, okay, so I'll try two methods. First of all, let us try to access this element by index. So how will I access it by index? Simply I'll do list, and I have to call 3. This will give me 40. Okay, so this particular thing is of O1 time complexity, because I know the location does not because I already know I want to locate the element which is present at third, correct? And if I want to access it by index, so it will be list 3, and it will remain O1. So here I'm not searching any of other elements. For example, this list could be of 100 elements. It does not matter, because I know that 40 is existing at 3, and I will access directly by calling 3. So this becomes O1 time complexity. So whenever you have to access any element through an index, that is particularly called O1 time complexity. So for example, if you see, accessing any element by index, you have this list, and if you access 0 or like whatever, you'll get the output, and this is the most easiest time complexity. A real world analogy you can think like, for example, there's a bookshelf. As I mentioned, there are a lot of books. You know that you only want to pick the book which is at the third index. So it does not matter what is the size of your whole bookshelf. It does not matter to you. All that matters is that the book that is present at third index, and that's how you will only address that particular item. So here time complexity will remain, it will remain to be O1. Now comes the second scenario, that what if you want to access this element by name? Okay, we have discussed this part earlier. For example, if we have to access any element by name, or let's say I want to know the index of that particular element, so how do we do that? We do a for loop. So it is generally of O(n) time complexity. That for what we do, that for a in list. So remember, how do we write the code? For example, that let's say this is list is equal to 10, 20, 30, 40, 50. If I have to access the element 40 by name and get the index, so what will I do? For I in range of length of list, okay, if list I is equal to, for example, let's say my target is 40, I know this, then print I, okay, and else. So we don't need else basically, right? So that's it. So we'll get the element 3. Now what it will do, it will check all elements one by one, and whenever it find 40, it will just print it. So what time complexity? We have discussed this particular thing earlier. This is called O(n) time complexity. Okay, so whenever you have to access an element by an index, that is called O1. And when you have to access an element by element name, then it is ON. So remember this particular thing. We will be using this extensively. I have mentioned all these details in the Python book which is present here, but just want to ensure that you guys understand the concept. Okay, now we will move towards the next part, that is how do we like appending elements. How does a time complexity change with appending elements? So let us say we have this task right now. We have this particular list and we have to append, add or remove element from the end of the list. So there will be two possibilities. One will be to add or remove from this end, and one will be to add or remove from this end. So right now we will talk about adding or removing from the right end. Now for example, let us say I want to append an element 60 to this particular list. Okay, so what will be happening? Let's say this is element. I will simply write down, let's say this is list, and I will say list dot append 60. Okay, so how does this work? That this particular list element will get added to this. Okay, we will get it here 60, and this will become index 5. So do you see that it was just one operation, and if I have to add anything towards the end, I don't need to visit any of these elements, correct? I will simply plug in an element here and it is done, and we will get the index. So this particular thing is of time complexity O1, because we are not touching any of the other element, correct? Now similarly, let's say I have to drop this element. So what I will do, I'll pop this up. So I'll say list dot pop. So what does pop do? Pop removes the last element. So if I apply the pop method here, it will remove this 60 from here, okay, and it will go away. This has not impacted any of the elements which are present from 0 to 4. Okay, so this is also O1 time complexity. So what have we seen here? Adding or removing an element to the adding or removing an element to the end of the list, has 0 O1 time complexity. It does not depend upon the length of the list. Okay, sounds very basic, but we need to understand it, because when we will be encountering bigger problems, we will see that this particular thing is very helpful. Okay, so if I just have to show you through code, for example, so let's say I have to do list dot append 60. Okay, so now what I will do, print list. So I have got 60. Now what I do, list dot pop and print list. So basically actually I changed the element list definition again. So let me do one thing, list dot append 60, okay, and print list. So now the list definition is this one. So what I will do now, list dot pop and print list. Okay, so we have removed this particular thing is of O1 time complexity, and this is also of O1 time complexity. Okay, so these both methods are removing or adding an element from the end of the list are called O1 time complexity. Now let us consider adding or removing from the start of the list. So now let us say I want to add this element 60, not here, I want to add it here at the start of the list. Now what will happen when I add this to the start of the list? So what will be happening? The list will become like this. If you notice that it will be 1, 2, 3, 4, 5, 6. So it will become 60, 10, 20, 30, 40 and 50. and indexes will become 0, 1, 2, 3, 4, 5. So have you observed anything that the indexes, for example, for 10 it was 0, now it has become 1. For 20 it was 1, it has become 2. So index for each of the element, when I am adding any element here, shifts by 1. Okay. So technically what is happening, that each element is being accessed and its index value is being changed. So when I am adding any element to the start of the list, I have to access all the other elements in the list. And this is a reason this particular task, and how to add this, we do list dot insert at 0 index, because I'm adding at the 0 index, I have to add an element 60. Okay, this operation is O(n) time complexity. This is very important to keep in mind, that inserting an element at the end is O1, but if I'm adding anything from the start, it is because all the indexes I have to reorder and reshuffle. That's why each of the element is getting changed technically, and that's why it is O(n) time complexity. So if I'm adding anything from here, it is O(n) time complexity. I hope this explanation is clear. So how to do this particular change? Simply, so let us say we have this particular list here. I will remove all this. Okay, now I have to add list dot insert at index 0, I'm adding 60. Okay, print list. Okay, so I added 60 here. So I hope this particular explanation is clear, where when I'm adding anything to the start, the time complexity is O(n). So let me clear the board. So this particular method is O(n) time complexity. Now let's consider removing anything from the start. Can you try to guess? Just pause this video for a second and try to think, what if I now from this, let's say this is my list. Now if I have to remove 60, so what will be the time complexity? So let us see. Now I have my list like this. 60, 10, 20, 30, 40 and 50. Now this element is 0, 1, 2, 3, 4, 5. Now if I'm removing this, so for example, let's say if I remove this, what will happen? Now this, I will be left with this, and now a list has to start with an index 0. So all these indexes are not correct, they will be reordered again, and the new list with the right index will look like this: 10, 20, 30, 40 and 50, and new indexes will be 0, 1, 2, 3, 4. So do you see that even if I'm removing from the start, my indexes are reshuffled, right? And it was 1, now it is 0 now. So now they are getting back by 1. Okay, so even this, so this element is done by list dot pop at 0 element. So this is also O(n). Again, popping from the end. So do you see that if you just write pop, this is O1, and if you write pop 0, it becomes O(n) time complexity. So this is very important to see. Correct. Now let's just do it from here. List dot pop 0. Okay, and print list. So I've removed 60. Now I'm left with this particular part. So I hope this explanation is clear, that when I, so let me just summarize what I am whatever we discussed in last couple of minutes. So let's say this is the list. Okay, so this is, let's say 10, 20, 30, 40, 50. 10, 20, 30, 40 and 50, and the indexes are 0, 1, 2, 3, 4, and let us say I have to add an element 60. So if I add this element here, okay, this will be O1, okay, and if I have to remove an element from here, that will also be O1. So if I'm adding or removing from this end, it is O1, and if I'm adding something here, for example 60, it is On, because all my indexes will be changed, and if I'm removing the first element from the list, then also it is On. Okay, so this is something you should keep in mind. I have covered this particular in the PDF that I have shared. The appending the elements, so see, appending elements will become O1, and inserting elements, if you're inserting, so we just discussed inserting at the start. Now we will also discuss inserting elements in the middle of the list. So now let's move towards that part. So far we saw that we inserted elements at the either end, either this end or this end, and we saw the time complexity. But what if we try to insert any element somewhere here in the middle of the list? What will be how it will impact the time complexity? So let us see that. Let us say I want to insert a number here in the center of the list, that is at the index number 3. So what will be happening is that my new list will look like, if you see that, it will be this one, and I will have 10, 20, 30. Okay, now let us say I wanted to insert the element 100. So 100 will be there, then there will be 40, then there will be 50, then there will be 60. And what will be the new indexes? 0, 1, 2, 3, 4, 5, 6. Okay, so what do we see that? For these 3 elements, the index has not changed. So basically, the numbers which are prior to the insertion point, their indexes have remained like they have not changed, right? But the indexes after that element, these have changed to 4, 5, 6. Okay, so these have not changed, whereas these indexes have changed. Okay, so what do you think time complexity will be? You will say that, okay, I see that for half of the elements my number have not changed, so I have not accessed each of them, like these elements, but I have changed for these 3. So what will I say? It can be O of n by 2, or we can say big O 1 by 2 times n. Correct? We can say that. This thought might come to your mind, but this is not On by 2, because there are 2 reasons for this. The reason is that whenever we talk about big O, we talk about the worst time complexity. Okay, now whenever I have to insert any element in the center of the in the center or somewhere in the list, it could be here, it could be here, it could be here, anywhere, I have to consider the worst scenario. Okay, the best scenario could be that, let's say I enter the list element here, and it will remain to be O1. That was the best scenario. But the worst scenario will be, what if I enter something at the start? There all the element list will be changed. Okay, and in big O we always consider the first thing, so it will be O of n in that case. And also, if you remember the previous video, we said that whenever we have constant in place of n, that constant is removed. Okay, so if it is O of 2n, or if it is O of 1 by 2n, all these constants can be removed. So overall time complexity of inserting any element in the middle of the list anywhere will remain to be On. And let us try to see how to insert an element. For example, let us say I have this list 50, 60, and I want to insert an element 100 at the index 3. What will I do? List dot insert, and it will be 0, index will be 3, and the element number is 100. And now if I print list, I will see the element here. So 1, 2, 3, 100. And this is what time complexity? This time complexity is On. So I hope this explanation is clear, that when we enter anything from this end, it will remain O1. When we insert anything from here, it will remain on, and when we insert anything in the middle of the list, it will still remain on time complexity. So I hope this particular part is clear to you guys. So let us try to understand these two concepts here. One is extend and second is concatenate. How does time complexity vary for each of the method depending upon what is the size of the list, how many lists are you using? First of all, let's try to understand what each particular method does. So for example, let's say we have this list. L1 is equal to 1, 2 and 3, and L2 is equal to 4, 5 and 6. If I do L1 dot extend L2, and now if I print L1, so it will give me a concatenated verb. Basically it will add these two into these particular, so it will create a single list of all these elements. Now what if I do, for example, L1, let's copy this particular same here. Okay, I do L3 equal to L1 plus L2 and print L3. Okay, let's say if I do this, if you see this was extend, so you see this is extend method and this is concatenate. Although these are producing the same result, but there is a slight difference between these two. Thing is that when you extend, you are technically adding elements to L1 only. So you technically are printing L1. Okay, there's no concept of L3 here. In the same list, you are adding L2. But when you concatenate, you don't extend any list. You create a new list, which is L3, which is equal to L1 plus L2. So we will try to understand how does time complexity vary. Now let us say when we are trying to extend a list. So we do L1 dot extend and we do, so for example, I do L1 dot extend L2. So what will be happening if you see that this list L1, I am not accessing any of its element, correct? Because I don't need to, I just need to add this L2 to this. So I will be adding a list which is 4, 5, 6. So what I will do, I will go to first number, I'll bring it here. I'll go to second number, I'll bring it here. I'll go to third number, I'll bring it here. So earlier my indexes were 0, 1, 2. Now my index is 1, 2, 3, 4, 5, 6. Okay, so this will become 3, 4, 5, the indexes. So technically the size of L2 matters to me in case of extension, because I am just extending L1. So the initial size of L1 does not matter when we do extend. So that's why whenever we extend, this time complexity is of O of M, where for example N is the size of L1 and M is the size of L2. Okay, so this is of time complexity of O of M. Now, and for right now it is 3, 3, so it will look like same, but it's actually dependent upon the size of the second list L2. I hope this particular part is clear. What we are doing here, the time complexity, so let's say this is of size M. Okay, so here time complexity will look like O of M. Let's say this was of size N, so N will not play a role here. That's as simple as that. Now when we are concatenating, but what happens when we concatenate two lists? So we are creating a new list. We are not technically we are not adding any element. So for example, this is 1, 2, 3. Let's say this was N and this was my L1, and let's say this is my L2 of 4, 5, 6, and let us say generate varies by M. In concatenation, I'm creating a new list L3 which is equal to, okay, I take each element one by one from this and I paste here, paste here, paste here. Then I take one element from here, 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 here. Okay, so technically I am doing M plus N observation. So that is why in case of concatenation, the time complexity becomes O of M plus N. Now M and n size varies, so technically this is the lowest version that we can bring it to. So this is here the time complexity becomes, if you when you add anything, it will become O of m plus n. So I hope the difference is clear. In case of extension, it is totally dependent upon the size of the later part which I am extending, correct? And in case of concatenation, size of both or whatever list you are concatenating, it matters. So this is the time complexity in this particular scenario. Now we will just consider one last part, that is if we are slicing a list. So for example, if I am slicing a list, how does my time complexity vary? So it's pretty simple technically. What happens, for example, when you slice a list, let's say there's a list L is equal to 10, 20, 30, 40 and 50. And let us say you do a slicing method. You do L from 1 to 3. So technically what you're doing, you're taking this element 1, 2, 3. You're taking these three elements and you are moving them to a new list, 20, 30 and 40. Okay, so here your time complexity becomes the size of this particular list. So whatever the size is, so it will become O of k, where k is the length of this particular element that you are fetching from. So I hope this is the technically big O of lists, how time complexity varies for each kind of step that you do. I have put a very detailed Python workbook for this. Just go through them one by one along with the video explanation and you will understand it. In the end of this, I have given 7 questions for assignment and you have to solve this, and the deadline to submit this assignment will be this Sunday. So these are pretty basic questions, not very complicated. Just go through. These are based on whatever we discuss in this particular video. So solve them, submit them the way you do, and you'll be good for it. So there are total 7 questions. So now I hope this particular video was clear to you, where we discuss what is the time complexity for big O of n. So if you have any particular doubt, as I mentioned, you can clearly comment below the video or you can reach out to me, and we will be starting with algorithms very this week only from Thursday onwards, and I'll hope to see you there. And thanks for watching this video. Please subscribe to Data Science channel if you have not, and I will see you in the next video.